Next up, we have Max Kuhn.
Hi, thanks for coming. So probably maybe to nobody's surprise, I'm going to talk about model tuning again. My job within the Tidyverse group is to work on kind of all types of modeling and how we can do that in a more tidy way. The place to start for us. Oh, sorry. Thanks. The place for us to start normally would be with more predictive models, but tidymodels infrastructure is not really constrained to do just that. We want to work on inferential models and descriptive models and all sorts of other things. Some of these models need what we call parameter tuning, and that's what I'm going to talk about today in this new package we have called Tune. So most of our tidymodels packages, in the Tidyverse, we don't tend to write like one huge package that does all the things in it. So we tend to write packages that are interconnected with each other. And so in doing so, before I can show you what Tune does, I have to show you what a few other packages inside tidymodels and how they work and how they feed into Tune. So if you've never seen tidymodels before, we're going to start with what I like to call the new Iris data, which is the Ames housing data. It's basically we have sale prices on houses in Ames, Iowa. That's what's shown here. We have data in different neighborhoods, and then we have all these features of houses, like their general living area, what type of building it is, and that kind of thing. So the goal here would be to predict what the sale price is of a house based on the characteristics of its data set, like the other aspects of the house. So let's say we were going to pre-process our data using recipes. So recipes, if you've never seen it, is a package that is really good at doing feature engineering and pre-processing every data before you put it in the model. And it follows this sort of this analogy of like baking a cake or making something to eat. So in a recipe, the first thing you start with when you look at a recipe is here are the ingredients into the recipe. So if we load the tidymodels package, that loads most of our sort of individual packages. So it's like a meta package. And then we can load the Ames housing data and create the data. So the initial recipe here, all it really does is says, the ingredients into our recipe is we have a column called sale price. That's our outcome. And then I just picked a couple predictors here to look at that are in this data set. And the recipe doesn't really do anything at this point. It's just beginning to say, here's a list of the specification of things we want to do. And the way recipes works is it's kind of like dplyr or ggplot, where you can just keep layering in things that you want to do to the data in the order in which you want to do them. So sale price is very much right skewed along with a couple other variables. So you can add a step to your recipe that says log in the data. You can use basic dplyr selectors, including like ends with and things like that, and you can tell it what base to use. Neighborhood that I highlighted in that map has some interesting characteristics where there are a few neighborhoods with only a handful of observations in the data set. So what happens sometimes is when you have a variable that is very unbalanced in its frequency, if you resample the data or so on and make dummy variables, it's very often you get some columns that have all zeros in the dummy variable column. So we have a step called step other that what it can do is based on a frequency cutoff that you use, for example the one here, you can say anything that has less than 5% of the training set in this neighborhood, let's dump that into another category called other, and then redefine our factor levels for that variable to have other in it instead of the original levels. So that's something you can do. You can make dummy variables. You see there's a recipe selector here that will select all the character or all the factor variables. And then based on that, you can add a few more things. We know from this data set that there's a linear effect between the general living area of a house and its sale price, both on a log scale, but we've noticed over time that different building types have different slopes. So that's an interaction effect, so you can specify interactions. You can also include splines. So if you do a plot of sale price versus longitude or latitude, you see these really wavy type relationships between these two variables. And instead of modeling these predictors in a linear way, you could use a natural spline, so step NS, to replace the original, let's say, latitude predictor with a basis expansion, like basically a couple of nonlinear terms that represent that data, and that allows that variable to be predicted or modeled in a nonlinear way. So if you ever use GM Smooth chances are, depending on the size of your data, you've used a spline to like figure out what that nonlinear relationship is. So what you would do with this recipe is you would apply these steps in a separate function call. You would apply these steps to your training set. It would do all these operations in sequence, and that would give you like a ready-made data set that you could then put into a model. So in terms of modeling, oh, and one other thing here is I chose, just based on looking at the data, to use 5 degrees of freedom for the spline. So lower degrees of freedom means it's less smooth, like linear, and higher degrees of freedom allow it to be more potentially smooth. All right, so you might think about using the parsnip package to do modeling. And if you've never seen that before, it's very similar recipes in that you make a specification of what you want to do before you actually do it. So let's say we just want to fit some type of linear regression model, like numeric outcome. We know we're going to have slopes and intercepts. That's like the structure of our model. So in parsnip, we have these functions that delineate, like, you want to do this type of structure like k-nearest neighbors, or linear regression, or like a neural network. So first you state what type of model you want to have, which is not really terribly descriptive, as you can see when we print it out. And then you'd state the engine. So the engine is basically what implementation do you want to use. So you might use an implementation that does Bayesian analysis to estimate your parameters, or like a robust regression and so on. So you have a lot of options. I'm going to choose GlimNet here, which is like a regularized regression model. But you could have used LM or Stan or Keras or all the things that we have implemented. And so now you've been a little more specific, saying we want to fit this structure of this model, but use this estimation to estimate parameters. And so I mentioned GlimNet does regularized regression. So there are also some other parameters that we probably should specify for GlimNet. For example, the amount of regularization, and this value called penalty. This is a fairly high amount of regularization. And then what GlimNet can do is it could fit 2 different types of regularization. It could fit the lasso model, which is like L1 regularization, or it could do ridge regression, which is like L2 regularization. And the cool thing about it is you can choose a mixture of these things. So if you're not sure whether you should be doing a lasso or ridge regression, you could try a mixture of the 2 to see if that works better for you than just purely one or the other. So in this call, I picked a fairly high amount of regularization and about a 50-50 mixture of lasso and ridge regression. And you can see when I print it out, it's there. But how do I know? Like, I have all these special numbers, right? Like 5 degrees of freedom, a penalty value of 0.1, and so on. So you might say, like, oh, he must have done a lot of analysis for this. But basically, I can't look at those numbers and say that's a great model. So the thing about this is we need to tune these values. Like, if you want to optimize our model performance, and we don't know what these values are, and there's no analytical function that says plug your x's and y in, and therefore it spits out a value of whatever for penalty. So we have to do something to find reasonable values of these parameters when we can't directly estimate them. And that's called model tuning. I'm going to show you the tune package in just a second. We have at least 2 ways of doing that model tuning. And what we're going to do is we're going to figure out ways of tagging, like which parameters do I want to optimize. Let's say I only want to optimize mixture and keep everything else the same. So how would we tell the tune package which actual parameters that we should optimize? Okay, so we're going to do that in a second. So I've been at RStudio for like 3 years. I've been thinking about this particular problem for like 20 years. And so when I started working on parsnip and recipes, I've been putting a lot of thought about, okay, how is this going to feed into the packages like tune that come later in the pipe? And so I was trying to figure out a way to summarize that this audience would understand maybe, or at least some percentage of this audience would get. And this is what I came up with. So if you've ever listened to Not So Standard Deviations, you'll know that, Hillary, if you're here, sorry. But a lot of really intense conversations about coffee, and that's how I've been thinking about this particular package. So okay, so let's say we load the tune package, but that'll be included in tidymodels. These are just the recipe and model objects that I just showed you. And so what we want to do is we want to say, which of these parameters do you want to optimize in some way to find good performance measures? So what we're going to do is we're going to substitute these actual values in with a function call called tune. And this function call doesn't actually do anything. It just returns an expression that says tune. Maybe not as happy as I just did. But the point is, if you've ever used recipes or parsnip, the thing is, when you create your recipe or you create your parsnip model object, it doesn't automatically just go ahead and fit those things. So we capture all these expressions and values. So we can add in a function value there because we haven't actually evaluated any of these arguments. So if we wanted to say which variables we're going to tune, we can actually, instead of putting a 5 in here, put this value in, and we'll do it for this one and this one. You can have actually other values that we keep constant if we like them. But then when we feed this into this sort of machinery of tune, it would understand which ones we should look at. And we've interlaced everything between recipes and parsnip and this other package called dials, where we've used like a common nomenclature for everything. So as you'll see in a little bit, there's a lot of like really good defaults of everything. So if you don't know like what range of penalty you should use or what you should be doing, we have a lot of fairly safe choices that you can use to automate the selection of like what grid you should use and what values and ranges. So these things all sort of work together. And if you want to specify as much as possible, you can do that. But if like you just want to let the machine figure it out, or if you feel like, oh, I don't know what I should do, our reasonable defaults are there to sort of do that for you. So one thing about this is we're giving longitude and latitude the same amount of like smoothness or wiggliness in the model. And we might want to like separate those out. Maybe longitude wants a little bit of smoothing and the other variable wants a lot of smoothing. So what we might do is we might say, well, let's create two different calls, and then we've given them separate identifiability. But the problem with this is when Tune parses this, it sees that there are two parameters called degrees of freedom that you're tuning, and it doesn't have a really good sense of like, well, how do I distinguish one from the other? So one thing you can do, whether you have this prop or not, is you can sort of annotate the names of these parameters. You can, like if you want to recognize them later and type something in that your boss will recognize if you show them some plots, you can add some ID fields here. So the one argument to Tune is basically an optional character string that this is how that particular parameter will be identified in plots and things like that. And it also lets you differentiate what this degree of freedom parameter is from this one. And so sometimes you would need to do this, but other times you might just do it because you want to use a name that like makes a lot of sense for you. So now we defined what we want to do. There's a couple different ways we could optimize these parameters. And the most like standard old school way of doing it, which I think works really well, is to use grid search. And in grid search, the ingredients to that is you need to have like some specification of like what you want to do, so your model and your recipe. And then you also need to have, or at least we prescribe you to have, some specification or some object that dictates how you want to resample the data. So what we don't want to do is we just don't want to take our data set, build a model with these parameters, and just repredict the data set. So whether it's like a separate single validation set or whether you do bootstrapping or tenfold cross-validation, a sort of required ingredient that we don't really have a good default for deliberately is some resampling specification. Optionally, you can define a pre-existing grid of candidates that you are in particular interested in investigating. But if you don't, we'll make some for you. And another thing we can do for you, but you can specify, is whether you want to optimize, I don't know, median absolute error or root mean squared error. So we have defaults for these if you don't want to go there. So what we're going to do is we're just really going to specify these two things. For resampling, we're going to use the RSample package. There's enough data here where tenfold cross-validation will be fine. The defaults here give you tenfold, and that's in this object. So our tuning parameters inside this function start with tune underbar. So tune grid does grid search. And then if you look at the arguments to that, here's our recipe and our model. Again, these are the versions of that have the placeholder in there for tune. Here's the resampling object that we need to specify. And then I wouldn't have needed to do this, but I just said, give me 10 tuning parameter values, like combinations of those 4 parameters to try based on what you know about these parameters and ranges that seem to be applicable. So again, you can define those things, but we've set most of these things up for you. And when you run that, you get this kind of intimidating object looking back at you. The first 2 columns here were already in the tenfold object. So that's what happens when you create a RSample resampling object. But depending on the options you choose, you get at least 2 columns with that. One's called .metrics and one's called .notes. You can see there are list columns with a bunch of tibbles embedded in them. So this has all like the RMSE values and R squared values across all the 10 models that we wanted to evaluate. And then that's for fold 1, here's what the results would be for fold 3, and so on. And so what we would want to do is, if we want to get at that data and plot it and investigate it, we would want to do some like dplyr or tidymodels unnest stuff to make that happen. Rather than like putting you through that and having to write that every time, we've written like a bunch of high-level accessor functions. So you can just say what you want to get and not have to worry about like looking up how tidymodels works and things like that. So some of them, not all of them, would include things like collect my metrics. So take all these tibbles that are nested and put them back into a format that I would like. And so what this does is, and let's look at the first 4 rows of that, is it gives you the tuning parameter values that you looked at. So for example, the first model used, the first candidate set used these 4 values, and its RMSE value is in log 10 units, is 0.0796. The R squared is almost about 80%. And then we have the second set of, the second combination of tuning parameters here and so on. So you might want to take these and sort them or plot them. Sometimes people just, they're in a hurry, they're trying out a bunch of different things. They might say, just give me the numerically best one. So let's say, give me the one with the smallest root mean squared error. And so we have functions like show best, which says, for this object, give me the one with the best RMSE. There's another one called select best, which actually just returns the parameter values. You can select on like the 1 standard error rule or other methods for doing that too. So there's a lot that we're not going into this second. Excuse me. There's an autoplot method that I'm fairly dissatisfied with. So this can only get better. Right now it shows the marginal relationships. So if I plot the latitude degrees of freedom against, let's say, R squared, you can see it's like really increasing and then tanks out here. Well, the reason it tanks out here is not because it didn't want that much smoothing. It's because the penalty value associated with that particular combination was really high, and that model didn't work so well. So what we need is a better visualization tool that could represent what's going on here in a way that people can look at things. If you've ever seen the Shiny Sand package, I've always wanted to create something like that. So my thought would be, if anybody wants to do that, on the plane ride home or something, I'm not going to, reject it. But an idea would be where you have your grid object and run like a Shiny Tune function on it, and it would open up a Shiny app that would let you maybe do some interactive investigation of these things. So I'm hoping that's where we go. It's not very hard to do. It's just a matter of one more thing on the list of things we want to do here. So there's some autoplot methods. They'll get better. So let's say you want to use the numerically best results, like just give me the one with the root mean squared error that's lowest. How would I weave that back into the original model objects and retrain? So what you would do is you would, let's say, select the best, and that would return this table of results. So it liked a very little amount of regularization. It's about a 50-50 mixture of lasso and ridge regression. It liked a lot of nonlinearity in the latitude and longitude data. And so, so if you're fine with that, what you can do is you can splice those values back into your recipe and into your model object. And so we have these finalize functions that if you give it the recipe that has the placeholders for the parameters and give it the best parameters, it just splices them back in as if you had specified them to begin with. So if you do that with the model and you print the model out, remember before it said 0.1 and 0.05, now here are the actual values to whatever precision we have that it thinks are best. And then you can just do the regular tidymodel stuff and refit this model and get to the place that you want to get to. So just some notes about that. There are these things called space filling designs in statistics. So these work really, really well. So it's easy for us to come up with good and pretty effective default grids for you using this type of model. There might be errors and warnings. And so in Caret and a lot of other modeling functions, across resampling, you might fit 200 models, and maybe one of those models gives 5 warnings. And so then when Caret's done running, it says, you had 2,000 warnings, type warnings to see the first 50, and you're like, right? And so there's no way to trace that back to, that was model 7 on resample number 3, right? So what we do is we catch everything as we go. So if you have a model or recipe that fails, it doesn't stop anything from computing. Then we capture all those warnings and errors as they go, and we can associate them back to specific things where you can go back and trace and see if oops, I just made a mistake, or there's some weird thing in the data. So that dot notes column is a tibble that basically has all that information in it. The verbose mode in this, I don't have the space to show it, but I'm really I use CLI, and so I think it's kind of cool. There's a bunch of options. So if you want to save the out-of-sample predictions, you want to save the model for each fold or the recipe, you can do that and show it here. There's options for all sorts of grid stuff and performance metrics. There's a lot I just sort of glossed over. Brian Lewis gave a great talk yesterday about for each and how to use that for parallel processing. So we use that here again. So whether you're doing MPI or you want to do multi-core in Linux, or if you're on Windows, you have to use do parallel. We have many options here to do parallel processing, which gives you a lot of speed ups in what you're doing. And I don't have time to talk about workflows, but workflows is another package we have where you can sort of bind together recipes and models and some other stuff together, and they're in one object, and this all works with that. So that was grid search. I have like a minute. So one thing that we did implement is, I'm not sure if it's like the best choice here for the types of models that non-deep learning models we fit, but iterative search, especially during Bayesian optimization, is a big thing. It's not really that hard to implement. And so what we have is you would start off with like a small number of parameter values, and I can feed in the ones I just generated. And basically what Bayesian optimization does is it takes those initial 20 points, it predicts a candidate set of values, of tuning parameter values it thinks would be best to try next. And you can see after the first 10, it predicts that you should try these. It resamples them. The performance was slightly worse than the original, and it just keeps going until either you run out of iterations or it doesn't see improvement after a while. This works pretty well. Its autoplot method doesn't stink. So, here's the initial set. One of them really did poorly. One of them failed, so you see a little gap here. So you can see over time, or over iterations, it's staying around the current optimum that we had. And maybe if it went further, I might be able to get a big boost. But that's the results. It's almost on CRAN. It's been like kind of rejected like 4 times for little things. So I'm hoping 5th time's a charm. If you want to learn more, it's packaged down site. Here are the training notes from this week, and we're working on a tidymodels book. So that'll be in our repo, probably in the next, the beginning of it in the next few weeks. So keep an eye out for that. Thanks.
All right, we got time for one question. Does tidymodels mark the end of Caret, or are there any plans for, e.g., Caret 2?
I'm going to get this like tattooed on my arm. No, Caret's not going anywhere. I mean, it's not. I swear to God, it's not. Because everybody asks me this question, and I'm like, it's not really. It's not like feature complete. I'm keeping up with it, making sure everything still works. I'm putting most of our development effort into tidymodels. Caret's 15 years old. So something that's like 15 years old, it's hard to make a lot of big feature changes to. So it's not going away. I wouldn't expect huge changes or new features in it, but it's doing pretty well as it is. So no worries there for people.
All right, we'll actually do one more. What about proper support for time series forecasting in tidymodels?
That's a great question. So I would think we want to do that. We tend to prioritize what we implement by things either we have like a huge increase in interest in or things we know a lot about. And I'm not really a time series guy. We want to do this, but it's a little bit lower priority because the stuff that Rob Hyman's doing is so good that we figure like you're not left with nothing right now if you want to use tidyverse type stuff with time series. So I think we'd like to use some of what he's doing there, but you already have something. So I think for the time being, unless somebody wants to implement and put in a PR or something like that, we're going to work on things that just don't exist right now before we get to those things.
Thanks so much.
Thank you.